Welcome back to multivariate calculus. In this video, we're going to be talking about flux integrals. Flux is a very important idea in the physical sciences. You more likely have heard of it in a pop culture reference. A lot of science fiction authors like to open up science textbooks, look for a word that they are not familiar with, and appropriate that word as a way of describing some futuristic sci-fi device that has no actual purpose in the world. The flux capacitor is far and away more commonly discussed than the flux of a hose, but the flux of a hose is what I'm here to talk about. In general, the idea of a flux is one talking about flow rate. I'm going to use the example of water flowing through a garden hose throughout this video, but we can think about anything that is flowing. A flux can be used to talk about the rate at which water is spraying out of a sprinkler into the air. A flux can be used to talk about the rate at which the air freshener is diffusing out after you spray it out of a can. A flux can be used to talk about the rate at which electrons flow through a wire in an electrical circuit. Mathematically, these all have the same basis. So let me get my head out of the way, and there we go. Get my head out of the way, and let's look at a zoom in on a garden hose. All right, so there's our garden hose, very elegantly drawn. And inside the garden hose, there is water which is flowing. And one of the interesting properties of a garden hose, or any kind of flow of water in any kind of tube, is that the water which is near the edge of the tube actually flows a little bit slower than the water that is near the center of the tube. And if you stop and think about it, that is something that can and probably should make sense. For water near the center of the tube, the flow of water is hindered by resistance in friction of the water rubbing against itself. Near the edges of the tube, the resistance is the water rubbing up against the tube. And the friction of water against rubber is going to be higher than the friction of water against water. So you will see a gradient of velocities in a tube. In a lot of applications, the specifics of that don't actually make any difference, because if you take the tube to be large enough, then you can ignore the part of the water flow that's against the edge of the tube where this happens, and you'll have a nice concentric ring in the center where things are flowing very nicely and very smoothly. You don't need calculus for that sense. So I want to look specifically here at the problem, where you have a relatively skinny tube, drinking straw size or something like that. Then there's not a lot of space in the center, and you have this problem spread throughout. All right, if this was constant, we could solve the question of flow rate using just algebra. How fast is the water flowing? Multiply that times the area of the surface, and you get the rate at which water is escaping. We don't have quite that luxury. So we have the rate at which water is moving is some function vector field f of x, y, and z, and we have the area of the opening of the tube. And we can calculate the rate at which water is flowing at every single point on the tube. We can add them all together, and we can calculate that the flux is the integral of my flow rate ds. All right, the symbol for flux here is a capital letter phi. You're used to the lowercase phi that we use to talk about the angle. Just put serifs on the top and bottom, and you go from the lowercase to the capital version. But there is one thing that we should take into account when we're thinking about how to set this flow rate up. The rate at which water is leaving the tube is going to be the same, whether you cut the tube at a nice right angle, or if you cut the tube on a bias. But if you add up the rate at which things are flowing through on the bias, we have a larger area. So the math wants us to have that this would be larger flux, but that doesn't make sense because the same amount of water is still exiting the tube. And so to deal with that, we're going to look at our normal vectors. And in order to get rid of that bias that comes from changing the angle at which we make things, we're only going to take the part of the flow rate which is perpendicular to the surface, or in other words, parallel to the normal vector. And we saw that the surface can be defined in a vector form by keeping in mind that normal vector. And the portion of a vector field which is parallel to a normal vector is calculated using the dot product, right? The dot product asks you for the component of the first vector in the direction of the second. And so that's what we've got here set up. When we've dealt with ds, area integrals for parametric surfaces in the past, we've dealt with them in scalar form. But we originally did get there by thinking about it as a vector first. We've been saying that ds is the magnitude of partial r, partial u cross partial r, partial v, dv, du. But there was no reason we had to take that magnitude. We originally set up ds as a vector that just had that cross product. Partial r, partial u cross partial r, partial v, dv, du. And that's the form we're going to be looking at here. Although in order to make this work, in order to make the mathematics possible, it turns out that that horizontal orientation is going to be problematic for us. So if I set up some x, y, z axes, I'm going to set up my hose parallel with the z-axis, perpendicular to the xy plane. And the reason that I want to do that is because that flow rate varied radially. So if I set this up in this orientation, I've got R measuring from the center of the tube to the edge of the tube. All right, so that's a hose with radius 1 centered on the z-axis. And I'm going to set up my flow rate, F. Instead of x, y, and z, it's going to be of r, theta, and z in cylindrical coordinates. And it's just going to be 2 minus r squared. Now my surface in question is going to be a circle of radius 1 at z equals however high off the ground this is. It doesn't actually make any difference, but I'm going to set this at z equals 1. So we're looking just a little bit up off of our ground level. I've got a couple of ways I can set that up. If I set my radius u and my angle v, then in rectangular coordinates, x is r times cosine of theta, which in this case is u times cosine v. Then we'll have u times sine v. And then we'll have z, which I've just set z equals 1. All right, my radius is 1, so I want u to be between 0 and 1. And my spin direction doesn't really do anything at all. So 0 less than or equal to theta less than or equal to 2 pi, one complete circle. Now, ds is partial r partial u cross partial r partial v dv du. And I'm really just doing polar coordinates going on here. So I'm not going to be surprised when I get u out, but I'll go through and do the calculations just to be safe. So we're going to have all right. I hat, j hat, and k hat. Partial of r with respect to u. Well, it's going to be cosine v, sine v, 0. Then I'm going to have minus u sine v, u cosine v, and 0. And when I set all that up, I'm going to get 0i, 0j, because those nice zeros in the z direction. And then we're going to have u cosine squared v plus u sine squared v in the k direction, and cosine squared plus sine squared is 1. So this is just u in the k direction. But knowing that it's in the k direction is important. So I get that ds is u k dv du. Now for my particular vector field here, I have my radius is u, my angle is v, so I'm just going to substitute in r equals u, theta equals v, but that doesn't appear. Z stays the same, but that also doesn't appear. So my vector field here is 2 minus r in the negative k direction. It's going downward. And that actually brings up an interesting question when it comes to doing flux integrals. My surface, I have set up so that the normal vector is pointing upward in the positive z direction. I know that my flow is going downward. I could just as easily have chosen that the flow direction or that the orientation of the surface was pointed downward instead. And if I had set up my choice of u and v in the other direction, it would have mathematically come out that way. The takeaway from this for our purposes right now is that the sign, positive or negative, of a flux integral is generally irrelevant. That depends on how you set things up. If you get a negative flux integral, that means that the orientation of your vector field and the orientation of your surface are opposite each other. If you get a positive flux integral, that means that the orientations are the same. We're going to have the orientation of the vector field is pointed downward. The orientation of our surface was in the positive k direction, that's pointed upward. And so we know we're going to get a negative result. That's okay, that's all that means. All right, but we have our vector field here. We can do our substitution. We have our ds. So we want to calculate the flux, which is the double integral over our domain of f dot ds. So it's going to be u goes from 0 to 1, v goes from 0 to 2 pi of our function was 1 minus, sorry, it was 2 minus, yeah. 2 minus r, but our radial direction was just u. So 2 minus u squared in the negative k direction, dot with u in the positive k direction, dv du. All right, well, k dot k is just 1. So we can split this up, we can clean things up. So we've got negative 2 minus u squared u dv du. Get all of our u's together. We've got 2u minus u cubed du. And we've got integral of dv. All right, so 2u minus u cubed. Integral there is going to be u squared minus 1/4 u to the 4th. And then we've got v going from 0 to 2 pi. All right, 1 minus 1/4, and then minus 0, and then 2 pi. All right, so 1 minus 1/4 is 3/4. Multiply that by 2 pi, you get 3/2 pi. So the flux of this particular hose is negative 3/2 pi. Again, negative just means that we set our orientation backwards of the flow rate, of the flow direction. Whether that's meaningful or not, you can go back into the geometry of the problem and figure out. The physics of that are beyond the scope of this course. Just figuring out how to set up and calculate the integral is the interesting thing here. All right, so with that, I would like you to try one. Get my head back out of the way. There we go. All right. There we go. We've got a vector field here. F of x, y, and z is equal to x, y, z. So vectors going off radially outward from 0, 0 pointed towards the direction of each individual point. And I've got here a surface, which is a rectangle parallel to the xz plane. So I've got 0, 1, 0, 0, 1, 2. I've got 2, 1, 0, and I've got 2, 1, 2. All right, so those are the four corners of this surface. It's a rectangle, so hopefully it's not too bad. But I would like you to think about how to parameterize that surface. And then once you have that, set up and calculate the flux integral. All right, take a couple of minutes, see what you can do with that, and I'll see you in the next video.